In this lesson, I'm going to explain how to interpret infrared scans. You'll be given the molecule structure. That's not something that you have to figure out. You'll know it. You must make assignments for the major characteristic absorption bands. There's 4 steps to follow. First of all, you want to look at the structure of the molecule. It's shown on the infrared scan. Write down every kind of functional group that you see in the molecule. Secondly, find the generic scan for that same type of compound. It's somewhere between page 105 and 115. Then review the wave numbers, the shapes, and the type of vibration for the absorption bands that are being identified in the generic scan. Step 3, go to the IR assignment tables. There, between pages 116 and 131, find every absorption that normally occurs for each of the functional groups that you've identified in Step 1 and Step 2. Note the wave number, where it occurs, and the type of vibration that's occurring. And finally, you can return to the infrared scan, locate the absorptions that you identified in Step 2 and 3, write down all these assignments in the correct boxes on the IR scan. Be sure to write the wave number that is listed in the assignment table, not the actual values that occur on that particular IR scan. We'll go through some examples to see what I mean. First example is isooctane. So step number 1, isooctane, notice, is branched. The groups that are present, and you want to identify them, there's a methine group right here, a CH group. There's a methylene group, just one of them right in the middle. There are 5 methyl groups in this compound, and there is this gem dimethyl group. The CH dimethyl is called a gem dimethyl. The word gem, as the word Gemini, means twin. Sometimes this is called an isopropyl group. And here it is right over here on the right side of the molecule. There's also this C-trimethyl group, which is referred to as a T-butyl group, right up here on the left-hand side. T-butyl, short for tert-butyl, short for tertiary butyl. We'll discuss this later. So those are the groups that we see in the compound. Step number 2, we get the generic scan. Now, the absorption bands for an unbranched alkane are shown in the generic scan below here. See, this is an unbranched alkane. It's just normal hexane. This is from page 105. Isooctane, our compound here, happens to be a branched alkane, so it will have some additional bands above and beyond what are shown in this unbranched alkane. Nevertheless, let's start here. So right from page 105, we see that the asymmetric methyl and the symmetric methyl stretches occur at 2960 and 2870, just below 3000 here. At the same time, the asymmetric methylene at 2925 wave numbers and the symmetric methylene stretch at 2850 wave numbers, they also occur in the same region just below 3000 wave numbers. So we generally get 4 bands that overlap and are not resolved or separated by the spectrometer. Now looking at this, you can see definitely that there's more than 2. So if we didn't know what this compound had in it, we could probably conclude safely that it has both methyl and methylene present in it. As well, on this unbranched alkane, we have the asymmetric bend of a methyl group at 1460, right here below 1500. And in the same location, we have the symmetric bend, it's a scissor type bend, of the methylene group at 1470. These are only 10 nanometers apart, and so they will not be resolved by spectrometer. They would co-absorb here. But there are a couple of unique absorptions that we can see. Around 1380 wave numbers, right here, we have the symmetric methyl bend, sometimes referred to as the umbrella bend, like an umbrella opening and closing at 1380, that uniquely identifies a methyl group. And notice it's right about the right location. Then Another unique absorption is for methylene groups. When you have 4 or more of these, you get a rock. It's a type of band called rocking. It occurs at 720 wave numbers. It's not very prominent, but it is sharp, and the more methylene groups you have, the larger it gets. So this is all the information we have from the generic scan. Third step is to go to the IR assignment tables on page 116 for alkanes, and look at all the absorptions for alkanes. So I'm just reading from the information that's on page 116. The paraffins are saturated hydrocarbons, and thus they contain only carbon-to-carbon and carbon-to-hydrogen single bonds, no double bonds. Now the carbon-to-carbon bends occur at very low frequency, below 500 wave numbers, and that doesn't appear in our spectra, so it's of no use to us. The carbon-to-carbon stretches, not the bends, but the stretches, occur at a higher wave number, but they're weak, and they appear over a broad range from 1200 to 800 wave numbers. And so they're of little utility, meaning they're of little value in identifying the particular compound. Let's flip back and take a look. For example, here we see between, say, 1200 wave numbers and 800 wave numbers. These are these carbon-to-carbon stretches. Now, they're not of much use to a human being. Perhaps a computer could identify the compound using this fingerprint area, much like a barcode can be read by a computer in a grocery store, but to people it's meaningless. But there are a variety of carbon-to-hydrogen stretches and bends that are of high utility. We can use them, and we've discussed them, and let's go through them again here. So the methyl groups in an aliphatic compound, an alkane, we have an asymmetric stretch at 2960 and a symmetric stretch at 2870, which will co-absorb. Likewise, the methylenes will have an asymmetric stretch at 2925 and a symmetric stretch at 2850, and all these four are co-absorbing. They're not resolved by the spectrometer. What is the intent of these lines? It's simply to say that these two bands are too close to be resolved. They would overlap, and these two bands are very close and would be difficult to resolve as well. All right, also we have at 1460 and 1470, we have the asymmetric bend of a methyl group at 1460 and the symmetric bend of a methylene group, and again these two simply overlap. They can't be resolved. However, at 1380 we have this unique symmetric bend, the umbrella motion of a methyl group. Notice here that that motion is a doublet in gem dimethyls and T-butyls. Okay, we're going to see that in our compound. We have what's called a gem dimethyl right here, this CH dimethyl, and it causes a splitting of the band at 1380, which is good information for us. At 720, we have the rocking of 4 or more CH2 groups, and that's true whenever N is 4 or more. If there's less than 3, that band at 720 moves to higher wave numbers, but the peak gets pretty small and usually can't be seen in any case. So all this information we already have from the generic scan, but in addition, we have in our compound, I already mentioned the gem dimethyl group, CH dimethyl. It's called a gem dimethyl, and it causes a unique absorption. Again, here it is on the right hand side. It causes the band at 1380 to split into a doublet. Let's flip back and take a look at that. Right up here, the band at 1380 is split, which suggests we have either a gem dimethyl or the other group that causes the same thing as the T-butyl group right here. The T-butyl group, this one right here, that's on the left, this carbon trimethyl is called tert-butyl, and it also causes the methyl group to split. So we got two causes of a splitting. We can't say, looking at the scan, which it is, but in fact we know both are present. In addition, this gem dimethyl has a unique absorption at 1170. It's due to a carbon-to-carbon stretch, and the T-butyl group has two unique absorptions at 1210 and 1255 as well, carbon-to-carbon stretches. Let's go take a look at those two, 1170 for the gem dimethyl, 1210 and 1255 for the T-butyl group, and we'll see them right here. So 1170 for the gem dimethyl, 1210 and 1255, very close to the actual values for the T-butyl group. So you see the table gives us more information than the generic scan. This last group is not part of our compound, so it doesn't apply. Alright, that's it. So step 4 is simply to copy these assignments into the appropriate boxes, and here I've done that. Methyl and methylene asymmetric and symmetric stretches. 4 bands co-absorbing here. Methyl and methylene bends, 1460, 1470, co-absorbing here. The unique band at 1380, which is split by both the gem dimethyl and the T-butyl. And then we have this carbon-to-carbon stretch at 1170 due to the gem dimethyl group, and the carbon-to-carbon stretches at 1210 and 1250 due to the T-butyl group. So notice that the wave numbers that we assign in these boxes, they are not taken from the tables. I did not write 1168 here. What would be the point? It's already shown here. What I want you to write here are the wave numbers taken from the tables, not the wave numbers listed on a particular scan. Every different hydrocarbon will have a slightly different wave number where a given absorption occurs, but on average it'll be close to the values from the table, and by writing these out on a regular basis you will start to be familiar, if not learn them, without really even trying. A word of caution here. You do not want to look for matching absorption bands by simply flipping through the pages of the generic scans. It seems to be a fashion among some students. You should look only at the generic scan that matches your compound. Don't assign functional groups that are not in the compound. You see, it does happen that certain absorption bands occur in a similar location as a result of different groups. For instance, an NH group and an OH group might be similar, but it's either one or the other. It can't be both. So the way to do it is to go to the scan that corresponds to the compound that you know you have and assign it. If you're wondering about the future, well, at some point in the 5th semester you'll be given an unknown spectra and have to identify it, but at that time you'll be given an IR, an NMR, a mass spec, and a UV absorption, and perhaps other information, and you'll use all them together to determine it. So at this point you know what the compound is, just find the compound that you know you have. Okay, example number 2 is one octane. So here's the structure of one octane. Notice it has a methyl group, 1, 2, 3, 4, 5 methylenes, and this terminal double bond on the carbon. So the structure reveals one methyl group, 5 methylenes, and one CH2 double bond CH. We call it a vinyl group, and it's a terminal alkene. Now, when an alkene double bond is at the end of a chain, it is described as a terminal alkene. It has different absorptions than an internal alkene, which is a double bond that is not on the end of a carbon. So this is useful information, as you'll see. Step number 2, we go to the generic scan, and here it is. And I'm simply reading what's in the notes. Alkenes, and this is important, alkenes will have all the same absorptions of a typical alkane. In other words, the CH3, CH2 absorptions here, the 1460, 1470 methyl-methylene bands, the 1380. We're not speaking to those. On this scan, we're simply showing what's different, what's unique to the alkene. So again, a terminal alkene has an asymmetric CH2 stretch at 3080 wave numbers. It's easy to distinguish this because the saturated alkenes have their absorptions below 3000. But an alkene has it above 3000. Terminal alkene at 3080, internal alkene at 3020. Easy to distinguish between them. Both of them are above 3000 wave numbers. Another useful absorption band The carbon-to-carbon double bond stretch occurs at 1650 for a terminal alkene right here. Easy to pick that one out. For an internal alkene, it's pretty close, 1670. May be hard to distinguish, but whether it's internal or terminal, at least you know it's an alkene. Also, there are some additional absorption bands somewhere in the range of 1000 to 730. Depending on what the structure is, we'll look at this in the tables. We'll get more information there. So again, the generic scan shows the same symmetric and asymmetric stretches and bends of both the methyl and methylene groups that we would see in most hydrocarbons. They're not listed on this table. They're just understood to be there. In addition, the terminal vinyl group displays some unique absorption bands. So now we go to the assignment tables. I'm just going to read what's here. In addition to paraffin bands, unsaturated organics show carbon to hydrogen stretching bands above 3000. They are rarely hidden by the strong main bands below 3000. That's good. No interference there. The carbon-to-carbon double bond absorbs sharply in the 1650 wave number region, as we said already, and the CH out-of-plane bends occur again somewhere between 1000 and 650 wave numbers. The exact position depends upon how the bond is oriented and where it's located. So here in our table, our assignments table, we see this terminal CH2 group at 3080 wave numbers, and it's an asymmetric stretch. That's what you'd write down. There is also an absorption band at 2975, but this wouldn't be seen. It always will overlap with the alkane, so I generally ignore that. The vinyl group, CH2 double bond CHR, that's our vinyl group on the end of a carbon, carbon-to-carbon stretch at 1650. And there are different absorptions for cis-trans tri-substituted. We'll talk about those later. Finally, there are some bends that occur. The bending of this vinyl group gives rise to 910 and 990 absorptions for this particular structure, CH2 double bond CHR, which is exactly what we have right on the end. So we can copy these assignments onto our scan. Again, we have our standard methyl and methylene groups just below 3000. The 1460, 1470 for methylene and methyl bends, and we have the 1380 methyl group stretch. So all those are the same, and even we have the methylene rocking at 720. But what's unique to the alkene is this asymmetric stretch of a methylene group, the vinyl group, at 3080. The 1650 carbon-to-carbon stretch for the carbon-to-carbon double bond of a terminal alkene. And then we have these carbon-to-carbon bends, CH out-of-plane bends at 910 and 990. Look how close they fall, 910 and 990. Almost right on the money. Okay, example number 3, final one, dichloromethane, aka methylene chloride. Here is the absorption, infrared absorption scan of dichloromethane. And notice what's in the structure. Step number 1, what do we see? We see one CH2 group, a methylene group, and 2 chlorides. And that is all, nothing else. Now, it turns out that halogens are rather difficult to identify by IR. Other types of analysis are much better at this, but we'll do the best we can with this. Now, I have no generic scan in the notes for a halogenated hydrocarbon, aka an alkyl halide, so we're just going to use the tables for this. So here are the assignment tables, and all I have is this paragraph here written. It's right at the bottom of page 116, right below the alkanes. The CH stretch is raised above 3000 in halogenated hydrocarbons due to the presence of electronegative halogens. For example, chloroform absorbs at 3010. If we go back and look at, well, let's go forward. Let's see. There's our structure here. Notice just above 3000, and that's due to the halogens on it, so it's higher than normal. The following carbon to halogen stretches are also observed. There's an aliphatic carbon to chlorine stretch that occurs somewhere in the range of 850 to 550. So that's a pretty broad range. Here's 850 to 550. Not very helpful to us. However, it is rather large. With several chlorine substituents, we have 2 in this case, the band occurs at a slightly higher end of this region. Notice it's closer to the 850. However, a carbon to bromine stretch, if we had bromine in this compound, it occurs at 690 to 515. So notice that's quite a bit of overlap with this 850 to 550. Say, for example, we had a band at 600, we wouldn't know if it's chlorine or bromine. And for that matter, carbon to iodine stretch occurs in the same kind of range. So again, 600 wave numbers could mean chlorine, bromine, or iodine. And for that matter, fluorine's not much better. So we know we have chlorine, so we can make the assignment. It is a large band. The band at 1470 from the methylene group has certainly dropped lower in this case. All alkyl halides will be identified in a later course by means of mass spectrometry, and you'll find that to be much more successful and satisfying. That's it for now. Good luck with that.